Hi everyone. In these series of videos, we will explain acid-base reactions. This is a very important topic in organic synthesis. Most syntheses require acid-base reactions in their last purification step. The material that you can refer to in this chapter is chapter 2 in John McMary. Now, don't forget, please, at the end of the chapter in the book, there are a series of problems. These are not a must. But these problems, you do have access to their solutions in the solution manual through Cengage Learning. So it won't hurt if you take a look at some of these some of these problems. You don't have to do them, but just take a look at them and see. Normally in the PowerPoint, I make sure to include everything that I want you to know, including a lot of examples. This is why the PowerPoints are a little bit longer than usual. There are two types of acids, Bronsted and Lowry acids and bases, and Lewis acids and Lewis bases. We brushed over this in 116. We talked about Bronsted and Lowry acids and bases. This is the first type of acids and base. And in order to have an acid, a Bronsted and Lowry acid, the acid needs to have an acidic hydrogen. That acidic hydrogen has to be linked to an electronegative element. The electronegative elements, normally they are oxygens, they are halogens. These are the most electronegative and strongest electronegative elements that make the hydrogen partial positive. And by definition, a Bronsted and Lowry acid has to have a partial positive hydrogen. So it must have a proton. Proton means a hydrogen. The more partial positive the hydrogen is, the more acidic is the acid. The partial positive hydrogen comes with the electronegative element. And the electronegative element over here, the higher the electronegativity of the element, the more it pulls electrons away from the hydrogen. And when it does, it's going to make the hydrogen more partial positive. So this is why if you have a hydrogen connected to an oxygen and a hydrogen that is connected to a chlorine, the hydrogen that is connected to a chlorine is more partial positive. So it's going to be more acidic than the hydrogen which is connected to the oxygen. Then you have the definition of Bronsted and Lowry base. And the Bronsted and Lowry base is a proton acceptor. In order to accept a proton, by definition, a Bronsted and Lowry base has to have lone pairs. Let me give you an example, like water. So Bronsted and Lowry base should have a lone pair. So from the oxygen, this is the Bronsted and Lowry base. By definition, the base uses its lone pairs in order to attack the acidic hydrogen over there. So the acidic hydrogen is partial positive. The base has lone pairs in there. This is basically the site that is electronically charged or electrically charged. It does have a lot of electrons in there. We call it a nucleophilic site. Nucleophile. This is a nucleophilic site. It does have electrons. The hydrogen is the site where it lacks electrons, and this is called the electrophile. So the electrons basically, or the reaction happens from the nucleophile to the electrophile. So the reaction happens from the lone pairs of the base to the acidic hydrogen whenever you make a bond. So in this case, I'm using the lone pairs of the base. This is my base. In order to make a bond with the acid, whenever you make a bond, normally you break a bond in this case. So by definition, an acid has to have an acidic hydrogen. The more partial positive the hydrogen is, the more acidic is the acid. The base has to have lone pairs or a site where you have electrons in there. Another site where you have electrons is basically if you have a carbon double bond carbon, or if you have a carbon triple bond carbon. This is also a nucleophilic sites, both of them, so they can donate electrons to take the acidic hydrogen. So a base needs to be a nucleophilic site. It can either have lone pairs or it can have a pi bond, one pi bond or two pi bonds in there. By definition, bases take acidic hydrogens. in Bronson and Lowry acids and bases take acidic hydrogen. Every time you form a bond, you break a bond. This is the rule. The different types of acids in there are different types of acids, different types of bases. Normally acids have hydrogens, all of them. Okay, now the more acidic the hydrogen is, the more the more partial positive the hydrogen is, the more acidic the hydrogen is. So this is why for H2SO4 you have to draw its Lewis structure just to see that the hydrogen is connected to the oxygen, not the sulfur. It's connected to the oxygen in there. Drawing the Lewis structure is very important. So both of these hydrogens are going to be acidic hydrogens that the base can come and take either one of those. This is a diacid. It has two acidic hydrogens. So if you lose one hydrogen, one acidic hydrogen to the base, you still have another acidic hydrogen, which is this guy over here. So this is the another acidic hydrogen that the base can take to form SO4 2-. Normally acids, to know them, they should always have a hydrogen. For Bronson and Lowry acids, and the hydrogen has to be partial positive, meaning that the hydrogen has to be connected to an electronegative element. So if you have, for example, CH4, okay, and I will ask you, the CH4 has hydrogens in there. Is this hydrogen acidic? Well, carbon is not electronegative to start with, because the electronegativity of carbon and hydrogens are the same. So these hydrogens in there are not going to be partial positive charges. So this is why these hydrogens are not going to be acidic. So the point is, not every hydrogen is an acidic hydrogen. An acidic hydrogen is a hydrogen that has to be connected to an electronegative element. Another way to know an acid is by the positive charge. So if you have an acid with a positive charge, then if you have any positive charge, then this is going to be an acid. Now, with respect to the bases, there are two types of bases. There is a negative charge base and there is a neutral base. The negative charge base normally is a strong base. The neutral base is a weak base, but both bases share the same thing. They have lone pairs. So lone pairs are a must for Bronson and Lowry bases, because Bronson and Lowry bases use their lone pairs in order to make a sigma bond with the acidic hydrogen when you have a reaction between an acid and a base. Now, every time you see a base, if it's negatively charged, it doesn't occur like this. It should have a positive counter ion to balance it, either sodium or potassium. In organic, we neglect or we don't show the positive counter ion, but you guys please know that these positive counter ions always occur just to maintain a balance in the charges. So if you don't see them in the reaction, this doesn't mean that they are not there. They are there. So for example, if you have a carbonyl, a carbon double bond O, see that lone pairs in there on the oxygen, you should show them. Normally I don't show them, but you have to show them in there. You have to know that there are lone pairs, and these lone pairs are the basic site. This nitrogen over here has lone pair. It is a basic site. This is a strong base because it is a negative charge. This is a weak base because it is a neutral. This is an example over here how to know Bronson and Lowry acids and bases. By definition, a Bronson and Lowry acid needs to have a hydrogen. So HBr is a Bronson and Lowry acid. NH3 in there, although it has a hydrogen, it can be an acid and it can be a base. If it is an acid, then it can be an acid from the hydrogen, but this hydrogen is going to be very weakly acidic because nitrogen is less electronegative than bromine or oxygen. So yes, it can be an acid over here. I'm just going to add that. So it is an acid from the hydrogen, and it is a base from the nitrogen. So NH3 acts as the double role, as an acidic part, which is the hydrogen, and a basic part, which is the nitrogen. Now CCl4, there is no hydrogen in there, so it's definitely not an acid. Which compound is a Bronson and Lowry base? To have a base, you need to have lone pairs. This guy here does not have lone pairs. It doesn't have any source of pi bond, so it is not a base. This guy over here does. See what I did? When I show you the question, I don't show you the lone pairs around the oxygen. You are responsible to draw the Lewis structure for it. So this is the Lewis structure in there. You see lone pairs around the oxygen. Oxygen is a negative formal charge. This is a very strong base. From the lone pairs, it is a base. It is not an acid. Neither one of these hydrogens is an acid because all of them are connected to carbons. This one over here, it is a basic site because it does have a pi bond. Now, let's classify those as acids, bases. Again, if you have a compound, the compound can act as a double role. Like for NH3 in here, it can act as a double role, an acid and a base. So if it has a hydrogen connected to an electronegative element, then this hydrogen is going to be an acid. And if it has an element that has lone pairs in there, and it doesn't have to be electronegative, just a site with lone pairs or a site that has electrons like a double bond or a pi bond, then it will be a base. This guy over here, it's not a base. There is no lone pair, there is no pi bond, and it doesn't have any acidic hydrogens. This site over here, this one over here, it has two oxygens there. See them? Both have lone pairs, so both of them are going to be base, the base site. So both of them can act as a base. Now, with respect to the acidic hydrogen, look at the carbon that is directly connected to the carbonyl. Normally, this one we call it an alpha carbon. The alpha carbon that is connected to the carbonyl has a special hydrogen, which is an alpha hydrogen. Look at the question in there. When you are given a condensed formula, see the condensed formula over here, you have to change it into either a skeletal or a structural, whatever you want to change it to. Here I kept it condensed, but I just added these bonds in there, and I showed you that the CO2, as we said last time, CO2 is a carbon double bond O. This is an ester functional group. So this guy over here is an ester functional group. This is an ester functional group there. Okay, now next to the carbonyl is a special carbon. This is called an alpha carbon. I'm not talking about this carbon. This is not an alpha carbon because it's connected to the oxygen. This one is the alpha carbon. So this alpha carbon over here contains an alpha hydrogen, and this alpha hydrogen is acidic. Why it's acidic? Because normally the base comes and takes this alpha hydrogen. When it takes this alpha hydrogen, what you create actually is a carbon, CH2, with a lone pair and a negative charge. This is going to be connected to the carbonyl. I'm not going to draw the rest of the molecule there. This over here is stable. Why? Remember chapter 1 undergoes resonance. It undergoes resonance in this case. It is a stable conjugate base because it undergoes resonance, and if it undergoes resonance, then its acid is going to be strong in that case. So this is going to be the resonance for it. If you have resonance, this means that you have distribution over a larger surface area. It makes the structure stable. If it's stable, then its acid is strong. So if you have a structure like this, always look at the carbonyl and the carbon connected to the carbonyl. If it has a hydrogen in there, this is an alpha hydrogen, then this is going to be an acidic hydrogen. So this structure acts as a double role. It acts as a base from the oxygen sites, and it acts as an acid from the hydrogen site. When you represent an acid-base reaction, always acids reacts with the bases. Acids does not react together. Bases do not react together. They will have no reaction. When you look at an acid-base reaction, it is an equilibrium reaction. This means that you should have the equilibrium arrow in there, showing you that it is a forward and it is a reverse reaction. So the direction of equilibrium is going to favor one side over the other. We will talk about this as we proceed. But always an acid reacts with a base to form a conjugate acid and a conjugate base. To locate your acid, always locate your acidic hydrogen. If one compound is an acid, the other one has to be a base. Bases should have lone pairs and a negative charge. It doesn't have to be a negative charge, but it's it should be it's either a neutral or a negative charge. Here in this case, the base is negative. This means it's a strong base. Here, the base is a neutral. Notice, base should have electrons, so this is the basic site over here. This is the basic site. Normally, nitrogens, oxygens, if you compare them, nitrogen is less electronegative than oxygen. So this is why nitrogen is more basic than oxygen. So this is why this structure also is a base, because it has a negative charge and because nitrogen is less electronegative than oxygen. The more electronegative the element is, the more it basically the more it attracts electrons, and it will cause the hydrogen to be more acidic. So acids and bases react with each other, and see how my arrow is. My arrow is from the base, from the lone pairs of the base to the acidic hydrogen. Now the base, as we mentioned, is the nucleophilic site. This is the nucleophile. For the nucleophile, we said that we're going to use the abbreviation NU. So we're going to use NU for the nucleophile from now on. So this is my nucleophilic site. It does have a lot of electrons. This hydrogen here is partial positive. This is my electrophilic site. This is the E+, the electrophilic site. Always reaction happens from the nucleophile to the electrophile. It cannot happen from the electrophile to the nucleophile. The reason why? Because the electrophile doesn't have electrons to start with. So how can you move electrons from something that doesn't have electrons? So the nucleophile is going to use its electron pair in a lone pair in order to make a new bond with the hydrogen, with the acidic hydrogen. So by definition, bases take acidic hydrogens. They take the acidic hydrogens. Every time you form a bond, so you're forming a bond here between the nitrogen and the hydrogen. This is the bond forming over there. Every time you form a bond, you break a bond. This is the rule in order to maintain low energy products. So you are breaking the bond in this case, and you're going to have a leaving group. So that OH is a leaving group. The electrons that are in this sigma bond, those are going to add in a form of lone pair to the oxygen. So this is why the oxygen has 3 lone pairs in this case. Same thing over there, the same thing over here in this example. Okay, so we've talked about those. We've talked about electrophiles. We've talked about nucleophiles. Reactions happen between nucleophiles and electrophiles. So let's go ahead and do this problem. First of all, we have. Okay, so first of all, let me magnify this a little bit. Okay, this is an example over here. Just let me bring it to front. So this is an example over here. In this example, you need to label the acid, the base, the conjugate acid, and the conjugate base. Your base in this case is the one that has the negative charge. So I know that this oxygen here is a basic site, but I cannot have two bases reacting with each other. And between a neutral base and between a negative charge base, the negative charge bases are the strongest. So this one is going to be my base. Okay, so this is going to be my base over there. So this is going to be my base. This means that this hydrogen over here is going to be my acidic hydrogen. The base is going to come, take the acidic hydrogen, and I'm going to form a leaving group. Whenever I make a bond, I break a bond, and you're going to get your conjugate acid and your conjugate base. Normally, again, as I mentioned, acids turn into conjugate bases. Bases turn into conjugate acids. So with this said, let's go ahead and do a problem. Let's see, where are we here? There you go. Okay, you return back this one here. So let's do this problem. So label the acids, the bases, the conjugate acid and the conjugate base. You start. This is an acidic hydrogen, so this guy is going to be my acid. This is going to be my base. There is a lone pair in there. This is going to be my basic site. So this is going to be my base. Okay, good. So now my reaction is going to be, you need to show the electron movement. My reaction is going to be from the base to the acidic hydrogen. This is my partial positive charge hydrogen. The reaction is going to be from the nucleophile to the electrophile. Always, every time I make a bond, I need to break a bond. So you need to show that the bond between the hydrogen and the chlorine is breaking. This bond is breaking over there. You have a lone pair over here. So it is breaking, and in this case, the oxygen will take the hydrogen. See, bases take acidic hydrogen, so it's going to take the hydrogen, and see what do you have now? You have an oxygen with the 3 bonds and the plus a charge. You won't have time to do formal charges. Please study the formal charge table in there. This is going to be my conjugate acid. How did I know? Normally conjugate acids have positive charges, okay? And then a negative charge is an indication of a base. So a positive charge is an indication of an acid, a negative charge is an indication of the base. Bases change into conjugate acids. Acids change into conjugate bases. So my reaction is going to be an acid plus a base is going to give me conjugate base plus a conjugate acid. B. Okay, so now I'm not, and this is what you're gonna see. I'm not gonna show you any lone pairs. I'm not gonna show you anything. So you have to figure out where is your acid and where is your base. Here, what you have is a NaOCH2 CH3, right? So let's go ahead and write it down. This is basically an ionic bond between the sodium, because sodium is group 1, it's a +1, and you have an oxygen in there with 2 carbons. That oxygen has 3 lone pairs and a negative charge. See, where is your base now? This is going to be your base. It is a strong base. So this is going to be my base over here. Let's go ahead and rewrite this and draw the lone pairs. You have to draw the lone pairs in there. As I mentioned, for every plus a charge, there is a negative charge to balance. Now, in some of the books, they will show you just the negative counter and negative part of the ion and not the positive counter ion. This doesn't mean that the positive counter ion is not there. It is there. Okay, and especially they don't show it to you in the product, but this doesn't mean that it disappears on its own. Remember that we should have balance of charges between reactants and the products. So if your reactants are 0 charge, your product has to be a 0 charge. See here, these two are 0 charges. So my product is negative and positive. These balance each other, so it's a 0 charge. Here, my reactant is a 0 charge. So my product has to be a 0 charge. So I should have a positive counter ion here. See that sodium? That sodium is there, even though we don't show it in the reaction. So that sodium is there and it balances the negative, so that I would have the total charges of the reactants and the products to be the same. It should be the same. It is a must. So if this is the base, this is going to be my acid. And as I said in the slide before, you look, since you have a carbonyl, you look at the alpha carbon. Alpha carbon has an alpha hydrogen, so this is basically a CH3. Okay, this is a CH3. It has 3 hydrogens in there. I'm just going to use one of these hydrogens. So my base is going to come and it's going to take this acidic hydrogen and it's going to form a lone pair over here with a negative charge on this carbon. And this is why you have a lone pair and a negative charge. This is a carb anion. It's called a carb anion. This is a carb anion. And that is going to be my conjugate base because it has a negative charge. Remember, acids are turned into conjugate bases, and bases are turned into conjugate acids. So it's a conjugate acid from the hydrogen. So the base always takes an acidic hydrogen and you form your product. See? Same thing. NaNH2. Na is a positive. NH2 over here, for nitrogen to make 2 bonds, it needs to have 2 lone pairs and a negative charge. 2 lone pairs and a negative charge. Since it's a negative charge, that guy is going to be a strong base. And if it is a strong base, it's going to react directly over here. So this is going to be my base. I'm going to put my lone pairs over there. This is negative, this is positive, this is an ionic bond. So that sodium won't disappear in the product, it is there. It normally balances any negative charge in the solution. This sodium, NaNH2 is called sodium amide, AMIDE. This is sodium amide. Sodium amide is a very strong base. So that base is going to take the acidic hydrogen. So where is the acidic hydrogen? See, I have a lot of hydrogens over there that belong to the carbons, and then I have a hydrogen that belong to the sp hybridized carbon. This hydrogen over here is basically pushed more towards the carbon, the sp, because the sp carbon is more electronegative than any of the sp3 carbons in there. See, this is an sp3 carbon with hydrogens. Okay, so this is an sp3 carbon. You have 3 hydrogens on the sp3 hybridized carbon over there. Compared to a hydrogen connected to an sp3 hybridized carbon and the hydrogen connected to an sp hybridized carbon, that hydrogen is going to be more acidic. So this is going to be the acidic hydrogen that the base is going to come and take. So this is going to be my acid. The rule says the reaction is going to happen from the nucleophile, from the base, the nucleophile, to the electrophilic hydrogen of the acid. Every time you make a bond, so now the NH2 will become NH3. Okay, you need to put your lone pairs in there. You need to put your lone pairs. Nitrogen, when it makes 3 bonds, it forms a lone pair. And then every time when you make a bond, you break a bond. And the electrons of these bonds are going to add to this carbon. So now this carbon is going to have 3 bonds. When a carbon has 3 bonds, and the lone pair, its a charge has to be negative, and this is why you have a negative charge. Please don't forget to balance your counter ions in there. So for every negative charge, there is a positive charge to balance it, especially if the reactants are 0 charge, then your products have to be 0 charge. This is another example over there. Please put your lone pairs on the oxygen whenever you see an electronegative element. H2SO4, this is sulfuric acid. So it's definitely an acid over there. Let's draw the Lewis structure for. Always draw the Lewis structure. It is not a waste of time. So draw your Lewis structure in there. Then you know that you have 2 acids, 2 hydrogens in there that the base can take. Just allow the base to take one of them. The reaction will be from the base lone pairs to the acidic hydrogen over here. You're forming a bond, you're breaking a bond. So you're breaking all of this, and the electrons of this bond will add to the oxygen. So now the oxygen in here will have 3 lone pairs. So if I want to draw the Lewis structure of this guy, then it's going to be an O with a negative charge. Practice drawing the Lewis structure, please. This is an S double bond O, and this is an OH. You can either write it like this, or you can write it as an HSO4 negative, but just know that this negative is on the oxygen. So it's kind of like deceiving over there. Where's the negative charge? It is on this precise oxygen, not on any other oxygen, it's on that oxygen here. So this is going to be my acid. This is going to be my base. This is going to be my conjugate acid because of the plus charge, and anyways the bases change into conjugate acids, and the acids change into a conjugate base. This is a conjugate base because it has a negative charge. This is a conjugate acid because it has a positive charge. So let me plug that in and move on. Okay. Another example over here, label the acid base, conjugate acid, and conjugate base. So let's go fast over here. So see in this example, what I did not give you the counter ion. I didn't give you the counter ion in there, but please know that there is sodium or potassium in there, okay? So normally we neglect it. Same thing as in this space, I didn't give you the counter ion, so there should be either a sodium or potassium in there. So every time you see a base that doesn't have a negative charge base, that doesn't have a counter ion, please go ahead and put its own counter ion there. And it's up to you to choose between sodium and potassium. It really doesn't matter. So this is going to be my base. This is going to be my acid. A carbon double bond OOH, this is a carboxylic acid group. So my acidic hydrogen is going to be this acidic hydrogen over there. This is my acidic hydrogen. So the reaction is going to occur, or it's going to happen as such. The base is going to come, it's going to take this acidic hydrogen, and the bond between the O and the H is going to break, and the lone pairs will form on the oxygen. So my product is going to be, this is a chlorine. My product is going to be a double bond O, and this is an O over there with a negative charge. See, I added a lone pair with a negative charge plus CH3. I formed a bond between the oxygen and the hydrogen. This is negative, so this is going to be my conjugate base. This is going to be my acid, my conjugate acid, and this is my conjugate acidic hydrogen. This is an example, another example, part B. Okay, this is my base. So B stands for the base, A stands for the acid. So this is going to be my acidic hydrogen over there. The base is going to come, it's going to take this acidic hydrogen, and it's going to break the bond, and the electrons of this bond are going to add to this carbon. So I'm going to end up getting my cycle, my triple bond there. I added the lone pairs, the negative charge, plus my hydrogen. The hydrogen is going to be a gas in this case. So I'm going to end up having a hydrogen gas. Now, please notice one thing. Again, see that negative charge? It's balanced with the sodium. So I have zero charge for the reactants. I should have zero charge in the product, so it should be balanced by sodium over here. Same thing for this guy over here. It should be balanced by sodium over there. So don't say where sodium is going to go into the products. Where is it? Is it here? No, it is not here. This is a neutral. That's it. A positive charge always is present wherever the negative charge is. And C, okay, in C, what I have is my my acid. This is my acidic hydrogen, so this is going to be my acid. How did I know it's an acidic hydrogen? Because the hydrogen is connected to a very electronegative element. So it's going to make this hydrogen more partial positive than a hydrogen connected to a nitrogen. So the more partial positive the hydrogen is, the more acidic is the hydrogen. And then you have your NH2. Now the NH2 is going to behave as a base from the nitrogen, so this is going to be my base. The reaction is going to be from the base, I didn't do the acid, from the base to the acidic hydrogen. So from the lone pairs to the acidic hydrogen over there, every time I make a bond, I need to break the bond. So the bond between the hydrogen and the chlorine is broken, and I would form a Cl leaving a group in that case. So now my product is going to look like this. I formed a bond between the nitrogen and the hydrogen. So I'm going to form my ammonium ion there. This is going to be NH3. This is going to be NH3. The hydrogen will add to the nitrogen. Plus the Cl leaves, right? So the Cl is going to be, it already has 3 lone pairs. So I'm just going to go ahead and add 2 more in here. These are my 2 more, and this is going to be my negative charge. Negative means conjugate base. Positive means conjugate acid. Okay, so here again, this is my acid. I'm just going to draw it like this time, HSO4 negative. So this is going to be my acid. This is going to be my base from the oxygen. So the rule says over here that I'm going to use my lone pairs of the base to take the acidic hydrogen, and I'm going to form my leaving a group in that case. So my product is going to look like this. This is an O, this is an H, this is an H, this is a lone pair, this is a positive charge, plus my HSO4 negative. Notice something. Reactants have 0 charge. Products, negative, positive, have 0 charge. I cannot stress this more. Reactants in the products, they have to have the same charges. They have to have the same charges. Draw the products for the following. So this is exactly the same thing. Let's go over it very fast. So you're having your base. This is the acid, so this is the acid, this is the base. The base is gonna come, take the acidic hydrogen, chlorine is going to leave. So you're gonna end up having the O, H, H, and the lone pair with a plus a charge, plus the Cl negative. Okay, I'm very sure that you can continue the rest. Here you go. So we have the lone pair over there. This is going to be my base. This is going to be my acid from the hydrogen. So my lone pairs of the base are going to come attack the hydrogen of the acid. The chlorine is going to leave, and we're going to end up having a hydrogen over here. This is a lone pair with a positive charge. See how am I maintaining my charges? Charges are very important. This is negative, so see, for every positive counter ion, there's a negative one to balance it to bring the total charge zero. Total charge zero, that balances the reactants. Same thing over here. Put your lone pairs, please. This is my base, this is my acid. So the lone pairs are going to attack the acidic hydrogen. Chlorine is going to leave, and you're going to end up having this guy over here with a hydrogen. This is a positive charge, plus the Cl negative. Okay, this is going to be my conjugate acid. This is going to be my conjugate base. I forgot to label those. This is going to be my conjugate acid. Positive means acid. Conjugate base, negative means a base. So this is conjugate base. This is conjugate acid. At the end, I believe this is more extra problems in here just for you to understand the idea. This is why I am doing this. Believe me, I'm not wasting your time. So here you go, because these reactions are really very important. We're going to hit on them in every single chapter. So the lone pairs attack. This is going to be my acid. This is going to be my base. And then a chlorine is going to leave. So you're going to end up having the nitrogen NH over here, NH2. Okay, it's going to be an NH2 because you added a hydrogen. Please maintain your charges. Keep track of your charges. It's going to be an NH2 positive because nitrogen should have a positive charge if it has 4 bonds, plus your Cl negative. And you see me every time drawing all the lone pairs when I am writing an organic reaction, because this is how it should be. This is an example over here how to draw acids and their conjugate bases. The rule is if you have a base and I ask you, just go ahead and change that into a conjugate acid, add a hydrogen to it. If you have an acid and I ask you change it into a conjugate base, you have to remove a hydrogen and it will be a conjugate base. So drawing the conjugate, this is the solution for these problems. Drawing the conjugate base for all of these, draw the conjugate acid for these bases in there. So if you want to draw the conjugate acid, just add a hydrogen to each one of them. This is easy. NH3 is going to become NH4 plus. Please maintain your formal charges. It's going to be HCl. Now this one over here, where are you going to add the hydrogen? You need to figure out where is your base. Where is your base in this guy over here? Because it's a base, right? So where is your base? So I have a carbon double bond O and it's connected to 2 CH3s. Now I know that these hydrogens are alpha hydrogens because they belong to alpha carbons. So these hydrogens are my acidic hydrogens, and my base is the oxygen, the lone pair on the oxygen. So to change that base into a conjugate acid, I have to add the hydrogen to the base site. So adding the hydrogen to the base site, it will become an O plus H. Now to change acids into conjugate bases, take away a hydrogen. So take away a hydrogen becomes Br negative, take away a hydrogen over there. Now true or false, you can, let's go ahead and see that. Again, the idea, if you have a base, you want to change it into an acid, add a hydrogen. If you have an acid, you want to change it into a conjugate base, remove a hydrogen. So for the first one over there, we have our base. We are adding a hydrogen to it. So that guy is saying is the conjugate acid of this guy. So this guy is my base. It's given that it is my base. and I want to see, is this my conjugate acid to it? Let's see. If I add a hydrogen to it, now this hydrogen is going to be my acid. I'm just going to go ahead and use a different color over here. So this is going to be my acid. This is going to be my base. If I am doing a reaction, the reaction is going to be as such. We will hit on this as we proceed. The double bond, it's a base from the double bond. So the double bond can be broken. So the double bond is going to break and it's going to take a hydrogen. When the double bond breaks and it takes a hydrogen, see, the double bond is two electrons that are shared between the p orbitals of these two carbons. When this bond is broken, then the electrons, because remember that when we talked about the p orbitals in there in the pi bond, and we said that the pi bond is whenever you have an overlap of the p orbitals in there, okay? So whenever you have an overlap of the p orbitals, that is my pi bond. So my pi bond has how many electrons? It has 2 electrons. When I say I'm breaking the pi bond, this means that I'm using the 2 electrons to make a new bond with the hydrogen, right? So when I am doing this, then the hydrogen is going to add to one carbon. So it's going to become a CH3, and the other carbon will lose electrons. It won't have electrons in there because the electrons that were shared before in the p orbital, I took them all out in order to make a new bond, a new sigma bond with the hydrogen to become a CH3. So the second carbon will be a positive charge. So yes, it is my conjugate acid in this case. So this one is a conjugate acid. It is a positive charge. For this one over here, I am starting with this conjugate. Okay, so I'm starting, this is the conjugate acid. So it's given that it is a conjugate acid. To form a conjugate base from this acid, just remove a hydrogen. This is my conjugate base. It's not this one, so it's false. In C, to start with, this guy over here is basic. It is not acidic because it has a negative charge. And in D, I'm starting with this acid, remove a hydrogen, and you're going to get this conjugate base. So it is true, and same thing for E. Now the strength of the acid, acids, they are classified based on their strength and based on how partial positive this hydrogen is. The more partial positive the hydrogen is, the more acidic is the acid. And the partial positive hydrogen basically comes with whatever group it is connected, the acid is connected or the hydrogen is connected to. So the hydrogen has to be connected to a very electronegative element for that hydrogen to be very partial positive so that the acid will be very, very acidic. So the idea is, this is the same idea as we said. So the more partial positive the hydrogen is, the more acidic is the hydrogen. It's the same definition as I'm saying, the more readily a compound donates a proton. So more readily the compound donates a proton means that the more partial positive the hydrogen is. Okay, so the higher the partial positive character of the hydrogen, so the more partial positive the hydrogen is. So the more partial positive the hydrogen is, the stronger is the acid. Now, in order to determine the acidity of the acid, we normally look at the equilibrium constant. It is the measure for the acidity. And the equilibrium constant, as in Gen Chem 2, it's the concentration of the products divided by that of the reactants. You already know this. Now, if you consider the dissociation of a weak acid, for the dissociation of the weak acid, we have HA plus water. That is going to give H3O plus A minus. So this is the dissociation of weak acid. So if I want to go ahead and write K equilibrium of the reaction, it will be the concentration of H3O plus multiplied by the concentration of A minus and divided by the concentration of HA and the concentration of water. We said that the concentration of water is always constant, so if we take that multiplied by K equilibrium, we're going to end up getting Ka, which is the acidity constant of a certain acid, and this is the equilibrium basically equation for it. Now, what I care about, I'm not going to ask you any Gen Chem 2 problems in there to calculate Ka or determine the acidity of the compound. We're not going to do anything of that. So no number calculations, but you have to understand the difference between Ka and pKa values. pKa values and Ka values, these are the measurement of how acidic the compound is. And the smaller the pKa, normally we work with pKa's because they are whole numbers. Compared to Ka values, they are 10 to the power numbers. So you're going to see a pKa table in there. There are different pKa tables that we're going to work with because not one pKa table contains everything. And these pKa tables, I'm going to point them out to you and you can use them in the exam. The smaller the pKa, the stronger is the acid. pKa values ranges from 5 to 50. This is one pKa table over here that you can use. As you can see over here, we are starting from the very strong acids, very low pKa's, very strong acids. Hydrogen iodide is the strongest acid in there. Of course, there are stronger acids than HI. There are acids that are -20, -30 pKa's in there. We would need two of those acids and we will talk about them as we proceed or in later chapters. So HI is the strongest acid, and then alkanes are the weakest. See, they are the weakest acids in there because the hydrogen is connected to a carbon and carbon is not an electronegative element. Between alkyne, alkene, and alkane, the difference here is how the carbon is connected to the hydrogen, or the type of hybridization that the carbon is connected to the hydrogen. So here you have an sp hybridized carbon connected to the hydrogen. Here you have an sp2 hybridized carbon connected to a hydrogen. And here you have an sp3 hybridized carbon connected to a hydrogen. Normally sp hybridized carbons, they are more electronegative. So this is why you see that triple bonds, hydrogens connected to carbon triple bond, these are more acidic than the ones connected to double bonds, than the ones connected to single bonds. This is one type of pKa table that we will be using. Another type of pKa table that we will be using, you're familiar with this table, and this table I'm going to include that on eCampus in the chapter 2 folder. So we are always also going to use this because there are some values in here that are not present in this table. Okay. So the idea here is rank the following compound in order of increasing acidity. We can use the table in order to do this. So for the table, you look for alkenes. This is an alkene. So you look for the alkene. You look for the carboxylic acid. Now, as I mentioned, this is a carboxylic acid group. See the acid? So I'm expecting this guy to be acidic. It is acidic, and anyways, it is very acidic. And the reason why it's acidic because it has resonance. We will talk about this as we proceed. So this is an acidic hydrogen there, and then you have your HCl. This is the hydrochloric acid. Get the pKa table values from the tables, from any of those tables, and then arrange the acids in order of increasing acidity. The lower the pKa, the stronger is the acid. Please remember that if the conjugate normally the trend for acidity is opposite for basicity. So if you have a strong acid, its conjugate base is going to be very, very weak. And if you have a weak acid, then its conjugate base is going to be very, very strong. This is how it works. Now, with respect to the direction of equilibrium of the reaction, since it's an equilibrium reaction, the reaction is going to favor one side over the other. And favoring one side over the other has to do with the acid and the conjugate acid. So you always look at the pKa of the acid, pKa of the conjugate acid to determine the direction of equilibrium. The direction of equilibrium is always away from the strong acid, from the strong acid. So it's always away from the strong acid. So the alkyne over here is a strong acid. This hydrogen here is a stronger acid than the hydrogen that is connected to the NH3. This is more basic. It's a more base than an acidic hydrogen. So so it has a lower pKa. The lower the pKa, the stronger is the acid. The direction of equilibrium is always away from the stronger acid. So the direction of equilibrium is going to be to the right. This is why when you draw it to the pointing towards the products. So the reaction will proceed as written in this case. Okay. Let's have an example over here. So we have water, we have HBr. Now figure out where's your acid, where's your base. This is going to be my acidic hydrogen. Then the lone pairs on the oxygen have to be my base. The lone pairs are going to come take the acidic hydrogen. Every time you make a bond, you break a bond. So the Br negative is going to be my leaving group. This is going to be my leaving group. That is going to be my conjugate base because it is negative. Positive, this is going to be my conjugate acid. Make sure reactants have zero charge, products have zero charge. Positive, negative, they balance each other. Now look at the acid and the conjugate acid. Always forget about the bases, okay? Because we don't have a pKa table. I didn't show you a pKa, a pKb table. Only I'm showing you pKa table, and we can figure out the direction of the reaction just using pKa's. So with respect to those two, hydrogen bromide is a stronger acid than the hydronium ion. This is called a hydronium ion. So your direction of equilibrium is away from the stronger acid. It is towards the products. So the reaction, we can say that the reaction will proceed as written. Here, see, this is water. This is going to be my base. This is going to be my acid. So this is my acidic hydrogen. This is my base from the lone pair. Base takes the acidic hydrogen, form a negative charge on the oxygen. So I'm forming my acetate. This is my conjugate base. This is my conjugate acid. Look at the acid and the conjugate acid. In this case, you should have your pKa's, the pKa's of these two. It should be in the table. In the table, I believe I have the HO3O plus in here somewhere. This is the HO3O plus. It says negative 1.7. So you guys, let's go ahead and change that. Instead of saying pKa 0, this is negative 1.7. So which one is going to be stronger? This is going to be my stronger acid. The lower the pKa, the stronger is the acid. So the direction of equilibrium is going to be towards the reactants in that case. What does that mean? This means that the reaction doesn't proceed as it is written. So you have to flip the reaction. So instead of pointing this to be your product, it is now your reactant. So when you write it down, you start with these two as a reactant, and these two form these two products. Let's have an example in here to end the section. So starting with a double bond in here, this is my source of electrons. So immediately this is going to be my nucleophile. It's my source of electrons, my pi bond that can be broken. So this is going to be my base. Sodium hydride, this is Na plus. This is H minus with a lone pair. This is an H minus. Sodium hydride is a very strong base. Very strong, this is very strong base. Wait a second. If this is a base, then here you go. I cannot consider this to be a nucleophile. Then I'm going to consider this to be an acidic hydrogen. See? Figure out where is your stronger base. I know that the double bond is a base. It is a nucleophile in there. But this is a stronger. So if this is a stronger, then this is going to act as my base. Then definitely this is going to be my acid. So I no longer look at the double bond in here. I need to look at this is my sp2, this is my hydrogen. So this is basically going to be my my acidic hydrogen. So the rule here says the base is going to come. It's going to take my acidic hydrogen and it's going to form a lone pair on the carbon. So the product is going to look like this. This is a carbon double bond, carbon. This is a negative charge over there. You do have your hydrogen, and then this is going to be my conjugate base because it has a negative charge. Plus, what happened here, the hydrogen took the hydrogen there, so I'm going to end up having a hydrogen gas. This is going to be my conjugate acid. Okay, so bases turn into conjugate acids, acids turn into conjugate bases. The question determined the direction of equilibrium, so you need to get the pKa of this alkene. The pKa of the alkene is 44. I'm using this table over here just to prevent me from switching back and forth between the slides. So pKa is equal to 44, and the pKa for the hydrogen is 35. This is the pKa for this hydrogen. So which one is going to be a stronger acid? This one is going to be, the lower the pKa, the stronger is the acid. So the direction of equilibrium is going to be towards the reactants. So the way that you draw it, instead of drawing this double arrow like this, you take this double arrow out, and then you just draw a long arrow pointing towards the reactants and a small arrow pointing towards the products. CH4, okay, so CH4 over there, let me draw it in another way. I always like to show my bonds, over there. So this is going to be my CH4. Now I know this hydrogen is not very acidic, but see what I have over here. I have an Na plus and an OH minus, which forces me to consider this as a base because it has a negative charge. It is a strong base. This means that this hydrogen is going to be my acidic hydrogen. Notice what I told you. This is not a very acidic hydrogen over there. So probably the direction of equilibrium is going to be towards the reactants, not going to proceed as written. So this is going to be my acid over there, and the reaction is going to be from the base, from the nucleophile to the electrophile over there, and then the bond is going to be broken, and we're going to add 2 electrons on the carbon. So we're going to have a lone pair, a negative charge, and then you're going to have all of these hydrogens in there, plus of course the water. You formed water in this case. So you formed a hydrogen here, you formed water. So let's see what do we have in here. Okay, so this is going to be my conjugate base, and this is going to be my conjugate acid. You guys remember what I said? Negative charge doesn't exist like this alone because this is a neutral. Then this should be neutral, then it should have a positive charge over here. The sodium is going to balance the negative charge. Now look at the conjugate acid pKa. This is 15.7. This is the pKa for water. For this acid over here, for the CH4, the pKa is equal to 50. Now this is going to be the weakest acid. This is going to be the stronger acid. So the direction of equilibrium is away from the stronger acid. So the direction of equilibrium is going to be towards the reactants. This means that the reaction needs to be flipped. You cannot write it like this. Okay? So another example over here. So far you know that this is an ionic bond. This is a negative charge. This is a positive charge. So this is going to be my base. This is going to be my acid. This is a carboxylic acid group here. So my reaction is going to be from the base. This is my arrow from the base to the acidic hydrogen. We're going to form a negative charge. Sorry, this arrow has to be, or has to initiate from the bond between the oxygen and the hydrogen. It will be broken and the 2 electrons will add to the oxygen. Now already the oxygen has 2 lone pairs. Already it has 2 lone pairs. So now I'm adding more. So now the oxygen will have 3 lone pairs. So here you go. So already it has 2 lone pairs and I am adding 2 more. This is going to be a negative charge now. Plus my conjugate acid in that case, and the conjugate acid is this guy over here from the hydrogen. This is my conjugate acid. This is going to be my conjugate base. and this is my base and this is my acid. Now take a look here. You can you can speed up the process a little bit. You have an acid and you have an alcohol. Which one is more acidic? Definitely it's the acid. It's going to be more acidic. So the direction of equilibrium is going to go towards the reactants. Let's go ahead and double check that. The pKa for the alcohol is 16. This is the pKa for the alcohol there. So pKa is equal to 16. And the pKa for the carboxylic acid, this is the carboxylic acid, is low. This is 4.8. So see, the direction of equilibrium is going to go away from the stronger acid towards the reactant, the products in this case. Here NaCl, you have to write it down in its ionic form. So the Cl is negative, right? So what is this, a base or an acid? It's a base. So this is going to be my base. Then this means that I don't care about the lone pairs on the oxygen, but I drew them. I am going to attack the base to the acid. So the base from its lone pairs is going to come, take the acidic hydrogen because this is my acid, and break the bond here and add the lone pairs to the oxygen. This is the basis to organic reactions. The basis to organic reactions, and if you understand this, everything else will be really easy. Reactions always happen between nucleophiles and electrophiles. See, when you form a negative charge, any positive counter ion in solution has to bond with it, there. So you have Na plus and O negative in there. This is negative, then this means that it is a conjugate base. This is going to be my conjugate acid. Direction of equilibrium, HCl has a pKa of basically -7. So pKa -7 here. This is my acid, this is my alcohol. The alcohol has a pKa of 16. You guys, if you are comparing an acid to an alcohol, definitely an acid is more acidic. The direction of equilibrium is going to be towards the reactants, a little bit towards the products.